Let's talk about probability tables, and specifically we're going to talk about simple, joint, and conditional probabilities. Using this table that you see, we have 400 individuals who 400 individuals that have two characteristics or two variables of interest in them that we've collected data on. Their gender, 250 of them are male and 150 of them are female. And then we asked them, if you were to buy a car, would you buy it mainly because of its appearance or mainly because of its performance? The letters A and P represent those two characteristics or those two events. There were 180 out of the total 400 people who buy a car because of its appearance and 220 who buy a car because of its performance. The breakdown or the contingency table, the cross tabulation if you will, is given to us. So we know that 120 of them, of the 400, are male men and they buy a car because of its appearance, and 130 of them are male and buy a car because of its performance, and those are the two subgroups that make up the total of 250 people. So let's talk about simple, which is sometimes called marginal probabilities. Simple or marginal probabilities are the probabilities of those the events that you see at work. The simple probability of being either a man or probability of being a woman, a female, and then the probability of buying a car because of its appearance or probability of buying a car because of its performance. So let's look. There are 250 overall total men out of the 400 group, the group of 400, and that computes to be 0.625. So I can actually go here and write this as a 0.625, and that's the probability that I've computed for being a man. Now, probability of being a female is complement of being a man. So 1 minus the 0.625, which is also which is 0.375, is the probability of female, which of course I can also compute by taking the 150, the total number of females, and divided by the overall total of 400, and that's how I get 0.375. So either way, I will get 0.375 as the probability of female. Now, with these red markings, I'm turning this frequency table into a probability table. Similarly, we can compute probability of buying a car because of its appearance. There were 180 people who bought a car because of its appearance, divided by 400, and we're going to get 0.45, and probability of buying a car because of its performance is 1 minus the probability of buying a car because of its appearance, and that's 0.55, which can also be computed by taking 220 and divided by 400. Either way, we're going to get the same answer. So these probabilities can be added in here. These are simple or marginal probabilities, and they can be written as 0.45 and 0.55. So now we have the simple or the marginal probabilities written in the margins of the table. Please keep in mind that we've already discussed complementary events. A and P are complementary to each other, and M and F are complementary to each other. We can also discuss mutually exclusive. If you're a female, then you cannot be part of the male men group, and vice versa. So female and male are complementary to each other. Similarly, A and P are complementary. Let's assume that in this study we've asked them to either specify appearance or performance as the reason for their purchase. Therefore, A and P are mutually they are complementary to each other, and also mutually exclusive. Let's now continue on and talk about joint probabilities. So far, in our analysis, we've only looked at one event at a time. Either we were looking at probability of male or female, or probability of appearance, or probability of performance. Now, what if we want to compute intersection? That's what your book calls it, joint probabilities or intersection of two events. Well, that's represented with a symbol, an inverted U, or horseshoe, and here we can find the intersection of two events, A and M, and that would be read as probability of A intersect M, or probability of A and M. A and M. So that is 120 people over 100. Over 400, the overall total, and that is 0.3. So we can see that the 120 people right here are both a male, and they are also buying a car because of its appearance. So that 120 has both of those characteristics present in it, and it doesn't make a difference whether I say probability of M and A, or whether I say probability of A and M. Either way, I'm looking at that group of 120, and 120 out of the 400 where fill that characteristic. So I can come in here and write the 0.3. Maybe I should erase first all the line I put around it. And so that's 120. And we have 0.3 as the joint probability. Similarly, we can compute probability of M and P, which is the same as probability of P and M. So the order doesn't matter. And that would be 130 over 400, which is 0.325. But also note that A and M and P and M are complementary to each other. So we have 0.3 and 0.325, which of course these two subgroups, the 0.3 and the 0.325, must add up to 0.625. And of course the frequency count of them also add up. The 120 and the 130 add up to 250. So these two joint probabilities, probability of A and M plus the probability of P and M, must equal probability of M. So similarly, we can now compute the other two joint probabilities, probability of F and A, which equals 60 over 400, which is 0.15, and probability of F and P, we can either compute it by saying that is 90 over 400, which is 0.225, Or another way of saying it, we can say this is equal to probability of F minus probability of F and A, which we computed above. So since the probability of F is 0.375, if I subtract probability of F and A, which I computed up here, 0.15, let me write that better. 0.15, then I can get the same 0.225. So if you understand these relationships, you can work your way in and out of these tables. So this is 0.225. So notice the 0.3 and the 0.15 add up to 0.45 in this first column. The 0.325 and the 0.225 add up to the 0.55 in the second column. And of course the 0.625 and the 0.375 equal 1, which is the total probability, all the 400 individuals. Also the 0.45 and the 0.55 add up to 1. And notice that all of the joint probabilities, everything written in here in red, add up to 1. And also notice that the first row, the probabilities add up to the marginal, it's written in the margin of it, 0.625, and similarly with the second row, it adds up to 0.375. So far we have talked about simple probabilities. We've talked about joint probabilities, and now we want to talk about conditional probabilities. So what I'll do is I will erase this some of this, or maybe I should just go a little bit further down and hopefully you have written this along with me as I've been talking about it, or maybe the second time you watch it you will be writing it down so you can refer back and forth up to the top of the page. So now we want to talk about conditional probabilities. Now conditional probabilities also have two events written inside of the parentheses, but in this case the order matters. Order is important. Okay? This sign that we write, it's not a slash, it's a horizontal, it's a vertical straight line, and the letter that comes, or the event that comes after the line, is the condition that must be satisfied. For example, if I write probability, open parentheses, then I put the letter M, then the given sign, and then if I put the letter A, this is probability of being a male given given the individual, given the person likes car for appearance. So this is the given, and that's how you read it. So therefore the letter that comes after the sign is the given or event, or the condition that must be satisfied. So how do we compute this? Since we are looking at given A, we're zooming in on this A column right here. Now we know there are 180 of them in there. So probability of M given A, we know there's 180 of them, so we should be dividing by 180. But look, M out of those 100, the males, out of those 180, there's 120 of them. So It's 120 males out of 180 people who buy a car because of its appearance. And if you go through that math, you get 0.667. So if we have 180 individuals who buy a car because of its appearance, and out of those 180, 120 of them are male, the balance, which is female, would give me the probability of being a female, given that you buy a car because of its appearance. And that number would be 0.333. And of course, these numbers add up to 1 because we're dividing the denominator, or the subgroup is comprised of 180 people, and the male and the female are the two subcategories of them. So they add up to 1. Now, by the same token, we can compute probability of male given that you buy a car, probability that you're a male given that you buy a car because of its performance, and that is 130 out of 220. Why? Because now we're zooming in on those people who buy a car because of its performance. And those people are 220 right here. So out of those 220, you can see 130 of them buy a car right there, buy a car because of its, I'm sorry, that out of the 220 who buy a car because of its performance, 130 of them are male. So 130 divided by 220 is 0.591. And probability of female given performance is 90 divided by 220, which is 0.409. And of course, these add up to 1. But so far we've looked at the given event being the reason for purchase, either appearance or performance. We can also compute conditionals for the other event. Probability of being, given that you're a male, what is the probability that you buy a car because of its appearance? And that would be, we have 250 male individuals, and out of those 120 buy a car because of its appearance, and that would be 0.48, and you can see that right here. 250 right here are men, but out of those 120 buy a car because of its appearance. Similarly, probability of buying a car because of its performance, given that you're a man, would be the remainder, 130 divided by 250, which of course would be 0.52, and those add up to 1. And we also have probability of buying a car because of its appearance, given that you're a female, and that would be 60 over 150, which is 0.4. And one more, probability of buying a car because of its performance, given that you're a female, and that would be the complement of this 0.4 that we just computed, which would be 0.6, but we can also compute it to be 90 over 150, which is the total number of females in this study. And of course, these two numbers add up to 1. These numbers are conditional probabilities, what we just discussed. And text insert. So let me go to here and let's talk about this problem in terms of a tree diagram. So if I have the two events of gender and purchase, reason for purchase, um, described like this, we can start by, in this case, we have all the probabilities of all the events, simple, joint, and marginal. So if I were to start with male and female, the probability of male we computed to be 0.625, and the probability of female is the complement of it, 0.375. So these two should always add up to each other because those are all the possible outcomes of this event gender. Now, the second set of probabilities that we diagram right here are conditional probabilities. And the reason why we say they're conditional because this right here would be the probability of, let's say, appearance given male, and this would be performance given male. Because the two events, let me start by like this. We'll get rid of these, and we'll say now that the two events underlying the reason for purchase are either appearance or performance. Appearance or performance. But these two events, notice that they come after the probability, the event of the customer being a male. So these two right here are conditional. Given that you're a male, what is the probability that you'll buy a car because of its appearance or performance? So this is given male, given male. And this is A and P given female, given female. Now we've computed these probabilities right here already from our table that I showed you before. And those are A given M is 0.48, and this will have to be 0.52. Even if I had not computed it, this would have to be 0.52 because of the complementary nature of them. And over here, A given F is 0.4, and so this will have to be 0.6. So so here we have simple, here we have conditional, and the rule is simple times conditional gives us joint. So 0.625 times 0.48 gives me the probability of A and M. Probability of A intersect M, which is 0.3. This one is probability of A or P and M. The individual is a man and buys a car because of its performance. So P and M was 0.325. And if you were to multiply 0.625 times 0.52, you're going to get 0.325. Oops. Similarly, over here we have probability of A and F, and probability of P and F. And those numbers are, if you multiply 0.375 times 0.4, you're going to get A and F is 0.15, and P and F is 0.225. Now obviously I told you all of those should add up to 1. Each of these numbers on these branches should add up to 1, and these two numbers on these branches should add up to 1. So at this point, coming back up here, let's take this tree diagram and let's flip it, meaning now we're going to start our first set of events to be reason, and we want our second set of events to be gender. Now reason, we can keep it to be appearance and performance, and gender can be man, female, male and female, male and female. But of course we know the second set of branches are conditionals. These two are conditional given A, and these two are conditional given P. So, and of course we know the end product of them. These are simple, these are conditional, multiply them, and we get joint. So even if I did not have all the information that I've already solved for, if I have this table down below on your screen, which I did first, I can work it backwards and generate all the information in a top table. The way I would do that is I know probability of A and M is 0.3, and A and M would be over here, A and M. So this is 0.3. This next one is P and M over here, 0.325, and P and M would be over here, and that's 0.15. Now notice the order has flip-flopped because the order of the tree has flip-flopped. So we had 0.3 up, and then the third entry, wait a second, P and M is 0.325, sorry, this should be 0.325. 0.325. Now notice we had 0.3, 0.325, now we have 0.3, skip one, and then 0.325, and that's because of the flipping of the tree. And now this one is probability of A and F, because we have individuals who buy a car because of its appearance, and they buy a car because of, and they are female, and so this joint probability would be A intersect F. And that number is right here, 0.15, and the last one will have to be the 0.225, which is the probability of P and F. Now once you have the end values or the joint probabilities, we know this. These two, which are at the end of this branch right here, will add up to that value. So 0.3 plus 0.15 is 0.45, which is what we had to begin with. If you go down in your notes, you will see that the probability of appearance was 0.45. And then let me change colors here. If I can, and I'll just highlight. And these ones, these two, will have to add up to this one. So the summation of those two will be 0.55, and I'll highlight that. Okay, so now that we have our simple or marginal probabilities at these first branches, and now that we have our joint probabilities, remember the rule: simple multiplied by conditional equals joint. So I can compute this probability right here, probability of M given A, by taking its joint probability, 0.3, divided by 0.45 to get 0.667. And similarly, I can compute this one. This is probability of F given A, which is probability of A and F divided by probability of A, which is 0.15 divided by 0.45, which is equal to 0.33. And similarly, you can compute this one right here to be 0.325 divided by 0.55, and this other one to be 0.225 divided by 0.55. And later on, when you see another video called tree flipping, I have 3 or 4 of them. This schematic of tree branching essentially is the basis of that analysis. I hope you found this helpful. I know this has been a long one, but I hope you've benefited from it. Thank you.